Okay, folks, for this screencast, I'm going to take the circuit playground and I'm going to measure the acceleration, and I'm going to make sort of like a pendulum here, and kind of see if I can plot that angle. Now, this isn't a perfect pendulum. This cable has some flexibility in it, and all of the mass is sort of distributed. If I was really going to use the pendulum equations, I would have to, I'll put this on like the end of a string or something. But I'm just going to kind of, show the way I did this. So if I move to this code here, so I'm just using the simple Adafruit Circuit Playground.express module that I imported. I'm using the math library to get the angle, and then I'm using time just to keep track of time. And so in this while loop, I get time, which I don't use, but I have there. And then I've got the XYZ acceleration values on this line of code here. Then basically what I do is I bring up the serial monitor. That's really fast. You can't hardly see. So basically, and here, you know what? Let me do this for you. Let me show you the X and Y values. So that first number is the X value, and the second number is the Y value. And you'll see that when I have the circuit playground like this, gravity is in the Y direction, and the angle is right around 0. If I move it this way, now the gravity is on the x-axis and the angle is -90. And so if I go the other way, now the angle is +90. So I can kind of just plot theta here. And so now I can kind of move it over to -90 and then over to +90 or 65 and go from there. And so if I get rid of the serial monitor and I pull up the plotter, I can see there's -90 and then there's some oscillations. Now it's not perfect. I mean, basically, let me unplug the CPX. This is what I'm looking for here, right? This plot here. Now this is not very great. For one thing, I'm only outputting at 0.1 seconds, so there's close to some aliasing happening here. But at least it kind of got the point across of like, there's the pendulum here. Now another thing I wanted to talk about is something called active filtering. So let me plug the circuit playground back in, and I'm going to, do serial, plotter serial, and I'm actually going to change this. What I want to spit out the instead of doing X and Y, I'm actually going to do X and Z. And so what happens is now what I can do is if I hold it flat, my angle is 0. And if I rotate this way, my angle goes to like -70. And if I rotate this way, it goes to +70. And so now I'm measuring the angle in this direction. Now if I increase the speed, get rid of the serial monitor, and bring up the plotter, now it's going to kind of race through. And this is what I wanted to talk about, because there's kind of a lot of noise in this that I don't necessarily like, and you can use what's called a complementary filter pretty easily to fix this. And so basically the way the complementary filter works is you have a theta filtered value that you have to assume as like an initial condition, and then you have a theta previous value which you also have to assume, at least in this case, is 0. And so basically what you do is you say your new measurement here, this is your new measurement, is this value here. You basically, get your new sensor measurement. So let me put here, get new sensor measurement. And then you process whatever data you need to get your measurand, I guess is what you want to say. And then you apply the complementary filter. Now I have a video where I derived the complementary filter. It comes from a common filter. If you haven't watched that video, I'll try and remember to post a link in the description. But basically what you're looking at is theta filtered is 1 minus S times theta new plus S times theta previous. And then what you need to do is you need to update theta previous with your theta filtered value. And then I can plot my theta filtered value as well. Now, it's going to throw an error because it's going to say that, hey, S is not defined. So what is S? Well, S is your filter value. There are two edge cases. If you make S 0, you're basically not going to filter at all because this whole term is going to go away, and you're basically just going to say theta filtered is equal to theta new. So if I save that and run the serial monitor, that's too fast for you to see. There is the data, and you can't tell that there's any different. And if I wiggle the sensor, you can't. You can't tell that those things are any different. So if I get rid of the plotter, if I do the other edge case, which is 1, this whole term will go to 0, and you'll notice that you're just saving the theta previous value. Well, the theta previous value is initially 0, so if I turn on the plotter, you'll see that that green line never moves. Okay, and the blue line is the raw value, and the green value is the filtered value. And so basically, there's this game here that you can play between 0 and 1. So if you apply, a little bit of filtering, say 0.1, right now, now you're going to see subtle differences between those two lines, and it's really hard to see what those differences are because you're barely filtering. The other thing that's happening is we're just cranking through these plots here. So I'm okay with this time.sleep here, but what I really want to do is I want to have like a plot counter. So I want to filter at the same speed, but I only want to print every 0.1 seconds. So I'm going to have a time step here that I'm going to call 0.1. And I'm going to say time print is 0. And I'm going to say if t, and I have to get this right, plus the time step. If time print plus the time step, if t is greater than that, then, and I'm going to do this down here because I want to use the measurement. I want to print the measurement, and then I also want to reset the time print to t. Okay? And so hopefully what that will do is it'll filter the same, but now it is only printing every 0.1 seconds. Okay? So like I was saying before, 0.1 is kind of slow. Let's do 0.05. 0.05. Okay. All right, so you can hardly see because my filter is so low, right? So if we crank up this filter now you should hopefully be able to see now what this filter is doing. Yeah, see, it kind of grabbed a little bit here, but it's still not doing enough. Let's go all the way to the other end. Let's go to 0.9. So now, see, there's that green line, and you see it's lagging behind quite a bit. Yeah, that 0.9 is really not doing it. Let's try 0.99. There we go. See, now we're definitely seeing something. So see this little blip here, it completely filtered that out. So there's like a high frequency spike, and that green line barely measured it at all, right? Now the interesting thing is if I put in a sine wave, you can see that signal completely lagged behind. And this is basically like a harmonic response. Like if you put a sine wave through a first order filter, you're going to get that change in magnitude, and you're going to get that change in phase. And so for low pass filters, which this is what this is, the magnitude and phase is a function of the input frequency. So if I put in a super low input frequency, you see the lag is maybe like 3 degrees, and the magnitude is almost the same. Now if I increase the frequency now you're going to see the magnitude is like a lot different, and the phase lag is approaching like 45 degrees. Now eventually, if I go too high, I'm going to completely filter that signal out, and the green line is going to be almost flat. I'm curious here. I feel like I don't know, maybe my computer is lagging. It's possible that's what's happening too. But what if we just print? Let me get rid of the plotter. What if we just print all the time and get rid of my little counter here? Don't do time monotonic, and let's just go as fast as we can. Now it's, oh no, data flood. I hate it when that happens. All right, let's throw a time.sleep in there. Sleep 0.1. Okay. Hang on. 0.1. Let's do 0.1. All right, there we go. Yes, that's way smoother. But you see, like that's look at that filter. See how slow that is when I like move from 0 to 90. So that's so 0.99 it was definitely too high. So you need to kind of, you know, tweak your filter a little bit. That looks way better. So now if I just leave this on a level surface, that's beautiful. So you can see all of those high frequency spikes are basically getting filtered out, and I'm getting, you know, moderate frequency response. Like, see, all those little blips are just getting completely filtered out, which is what I wanted. And I'm getting, like I said, I'm getting a little bit of lag, you know. And that kind of reminds me of a square wave, like a square wave duty cycle. So like if you look at like what an RC filter looks like, you know, you have this slow rise and this slow decay there. And again, you see this high frequency spike is just completely filtered out. The reason why the data stream stopped is because I unplugged the USB port. I know you're not supposed to do that, but it's the easiest way I find to stop the data stream. So anyway, so there is active filtering on real hardware. These 3 lines of code they're in my opinion, they're language agnostic, I guess is the word I'm looking for. You're just using multiplies and variables. So this code could easily transfer to MATLAB, to Python, to C, to Fortran, whatever. So you can implement this on any hardware you want, and you won't have any issues. So hopefully this helps if you ever need to put a complementary filter on a circuit, and then hopefully the beginning part of the video helped you with you know, acceleration and pendulum mechanics for the CPX. Anyway, I hope you enjoyed this video, and I hope you have a good night.